Hello, here's the second in an occasional series of practice integrals for you to attempt. So here's an integral, it's an indefinite integral, and you might be put off a little bit by the relatively large numbers here and here, but if you think about it for a moment, I hope you'll realize that they're actually giving you a friendly hint. So have a go on pencil and paper, and then you can come back and look at the answer. So I'll pause the video for a moment and suggest you do too. Welcome back. Let's go on and look at the next slide. Okay, so here is our integral, and I can imagine somebody looking at this and one of their first thoughts might be to use integration by parts because the integrand here can be factored into two terms. But I'll show you on the next slide after I've solved the integral that really isn't the right thing to do at all. So integration is all about pattern spotting really, and you get better at that through practice. And the pattern to spot here is that the factor outside of the cosine is essentially the derivative of the argument of the cosine. So the argument of the cosine is x to the power of 99, and if you differentiate that, you would get 99x to the 98. So x to the 98 is proportional to the derivative of the argument. And once we've seen that, we think about the chain rule, or the function of a function rule, as it should perhaps better be called, and we realize that we can have a guess at what this might be, and then we'll write out the guess with a bit of a space in front. I wouldn't normally put the dots, I just put a space, and then we'll work out what should be there afterwards. So what should it be? It's going to have to be something very simple, and it's going to be something where we're going to use the chain rule. So it is going to be a function of a function of x. It cannot be a product or anything like that, because if we differentiate that, we're likely to get multiple terms, and there could be a miracle and they all combine together, but that's not very likely, and we're not going to guess it in particular. So here we have the cosine of x to the 99. My guess is that it's going to be the sine of x to the 99. And we never, ever change the argument. So the argument of the cosine is going to be the argument of the sine here. So let's think now. If you integrate something, your answer is going to be something which, if you differentiate it, gives you the original integrand. So if I differentiate the sine of x to the 99, well, if I differentiate sine, I'm going to get the cosine. And that's great, and I don't change the argument, so I'll have cosine of x to the 99. And then what I will do is because I'm using the chain rule, I will multiply by the derivative of the argument of the sine. So I will multiply by the derivative of x to the 99, and that would be 99x to the 98. Well, x to the 98 I love, but I don't have a 99 here. So I can easily fix that by writing here 1, I'll just change the colour, 1 over 99. And now, if I differentiate this, I'm going to get the cosine of x to the 99 multiplied by the derivative of this. That will be 99, which will cancel with that, times x to the 98. So I will be left overall with x to the 98 times the cosine of x to the 99. And that is exactly this integrand, so we've written this down correctly. So this is called integration by inspection, and it's my favorite method of integration. So this is integration by inspection. And just to give people a bit of confidence in this, I'm just going to do the differentiation that I talked about a moment ago to show that it is correct. So if I want to differentiate 1 over 99 sine of x to the 99, I can pull the 1 over 99 through the derivative, and I then differentiate sine of x to the 99, and from the chain rule I get the cosine. I don't change the argument, you never do, and then we multiply by the derivative of the argument. So that's, when we work this derivative out, is going to give us 99x to the 98. So what we're going to get, just putting those numbers in front, is 99 over the 99 that's there already, times x to the 98 times the cosine of x to the 99. And we see that these two terms cancel, and we recognize here exactly the answer we want, the original integrand. So we are happy. So that's, in many ways, I think, the nicest method of integration, just if you can just guess what the answer is. And very often, I think, if you've shown such an integral, what you might do is you might start saying, well, I'm going to define a new function, u to be x to the 99. Such things are sometimes needed, but for something as simple as this, integration by inspection is much nicer. So I hope that's been useful, and on the remaining slide, what I'm going to do is just talk about why integration by parts would not be helpful. So finally in this video, I want to talk about why integration by parts is not a good idea. And integration by parts is a completely valid and good method of integration, but it is the method of integration that tends to be most overused by students in my experience. So what we do with integration by parts is we look at the integrand and we factorize it into a term that we're going to differentiate and a term that we're going to integrate. So you might think, well, if I differentiate the x to the 98, that's going to become a smaller power of x. That sounds good. But then you're going to have to integrate this. And I don't know about you, but this looks like a very difficult function to integrate. And it's certainly well beyond school level mathematics, and it involves functions that you first meet at university level. So I'm just going to say no, we're not going to even think about integrating this. It's horrible. And to be honest with you, the reason why I put big numbers in here was really just to make this something that you are less likely to use parts with. Okay, so let's just go back and look at it the other way around. Say, well, we'd integrate this and we'd differentiate this. And then remembering the integration by parts formula, we're going to need to integrate this. So that's going to go up to a power of x to the 99 over 99. And then here, when we differentiate that, we're going to get minus sine of the same argument, x to the 99, multiplied by, using the chain rule, the derivative of x to the 99. So the integral that we would get is going to look something like, so we would get, or we would need, something like, and there'll be some numbers which I'm not going to bother, you can trace them out if you would like. So it's x to the 99, and that has come from integrating v prime to get v. So we've increased the power by 1. And then when we differentiate this using the chain rule, what we're going to get is something like a minus sign, and there will also be numbers, but we'll worry about that later. The sine of x to the 99, remember you never change the argument, and then we multiply by the derivative of x to the 99, and that is going to be a 99x to the 98 dx. So you can see that the number of powers of x here outside of the trig function, which has the same argument as ever, is now going to be x to the 99 times x to the 98, so that's x to the 197. This is not getting nice. So this is not a method of integration that would be appropriate for this. So we definitely would not want to use integration by parts here. So just to summarize again, what we've done is we've used integration by substitution, and the reason we were able to do it is that this is essentially the derivative of the argument of the cosine. And because of that, we were able just to look at the integral and write the answer down. And with that, I'll stop the video.